Okay, in section 9.4, we're going to begin talking about sequences of numbers, and this is something that you've been dealing with your entire life in mathematics. 1, 2, 3, 4, 5, that is a sequence of numbers. 2, 4, 6, 8, 10, that is a sequence of numbers, and it doesn't necessarily even have to be patterned in order for it to be a sequence. It just has to be any set of numbers in a specific order. And so each element in that set is called a term, and we number the terms by using what is called an index. And so what I mean by that is a sub 1 means that that's the first term because of the subscript 1 there. A sub 2, that means the second term in the sequence, and so on and so forth. And so this is going to be our discussion of sequences. This is going to lead into section 9.5 when we talk about series, which is just the sum of the terms in a sequence. But I'm getting a little bit ahead of myself. We're going to talk in this section about explicit and recursive formulas, about arithmetic and geometric type sequences, and hope you guys enjoy the ride. Okay, before we get any further, let's distinguish between what an infinite sequence is versus a finite sequence. An infinite sequence, I say here that the domain is the set of all positive integers. But let me explain further what I mean by domain. I mean, when I say domain, the term numbers. And so what I'm saying is that when we discuss sequences, the domain is the term number. So we might say the first term is 5. Well, 1 would be the domain, 5 would be the range. So let me write that down so maybe it's a little bit more clear. A sub 1 is equal to 5. That 1 is like an element of the domain, and 5 is the actual term itself in the sequence. And so an infinite sequence means that you are having infinitely many terms in your sequence. And so you can see in these examples, the ... at the end is indicating that it is an infinite sequence, as opposed to a finite sequence, which consists of only the first certain number of terms, which we'll use n to represent, the letter n. And so in this example, 5, 10, 15, 20, 25, there are 5 terms in that sequence, so it is a finite sequence with n is equal to 5, and I could pull out what some of these terms are. So for example, a sub 3 would be the third term in the sequence, that would be 15. A sub 5 would be the fifth term in the sequence, that would be 25, and etc. So a finite sequence means a sequence that stops after a certain number of terms. Okay, the first type of sequence that we want to talk about is an explicit formula. And so an explicit formula is nice because it gives you the sequence as a function of the number of terms, which means in order to find a certain term, all you have to do is plug in the term number, and the formula will spit back what the term actually is. And the terms are independent of each other, which means I don't need to know what the 5th term is in order to know what the 17th term is, and so on and so forth. And so here in example 1, we're going to find the first 4 terms and the 100th term of these sequences. And so if I start with letter A, if I want to find the first term, that's going to be a sub 1. And to find that, I'm just going to replace n with a 1. And so 1 squared minus 1 will give me 0. If I want the second term, I'm just going to replace n with 2. And so 2 squared minus 1 is going to give me 3. A sub 3 will be the third term. That will be 3 squared minus 1, which will give me 8. A sub 4, you are starting to hopefully get the picture here. 4 squared minus 1, which will be 15. And then if I want the 100th term, then just like before, I'm going to plug in 100 for n, and that's going to give me 9,999. And sometimes we will write the answer in set notation as so. So we might say 0, 3, 8, 15, and then ... and then put 9,999 in there, and you wouldn't really be able to tell that that is the 100th term, and so this notation that I started with before is probably better than the set notation, but you might see it either way. Now for letter B, we have a sub k is equal to 3 plus negative 1 raised to the k power. And so the first term is going to equal to 3 plus negative 1 to the first, which will equal to 2. A sub 2 will be 3 plus negative 1 squared, which is going to be positive 4. The third term is going to be 3 plus negative 1 cubed. Negative 1 cubed is negative 1, so this is going to be 2. And a sub 4 is going to be 3 plus negative 1 to the fourth, which is going to make that positive 1 plus 3 is equal to 4. And then if I want the 100th term, I'm going to do the same thing, just plug in 100 for k, and this is going to give me 4. And so there's going to be some patterns sometimes. So like for example in letter B, I can see that this is a repeating sequence, bouncing back and forth between 2 and 4. And in fact, the better technical term is that this is an oscillating sequence. And so we're going to see that word later on whenever we talk about the limit of a sequence. But this is an oscillating sequence. I can see that every odd number term is going to be 2, and every even number term is going to be 4. And so sometimes you'll come across patterns like that that might help you out a little bit. Okay, a sub 1 for letter C. I'm going to plug in 1 for n, and that's going to give me 1 times 0 times negative 1, which is going to, of course, be 0. A sub 2 is going to give me, let's see here, 2 times 1 times 0, which again will equal to 0. A sub 3 will be 3 times 2 times 1, which will equal to 6. And a sub 4 will equal to, let's see here, 4 times 3 times 2, which will equal to 24. And then if I want the 100th term, then that's going to be 100 times 99 times 98. And so just plugging that into the calculator real fast, you get 970,200 as your 100th term. So explicit formula, pretty straightforward. If you want any term, you just plug in the term number, and the formula will give you what that term actually is.